Usually when we talk about a medical diagnosis, there's this expectation of total precision.
Right, like engineering.
Yeah, exactly. Like you break your arm, the x-ray shows that jagged white line, and the doctor just points and says, there it is.
It's binary, broken or not broken. It's clean. And it's comforting because we really like things to be visible and easily categorized.
You do. But then you step into the world of, say, neurodevelopment or maybe complex autoimmune diseases, and suddenly that x-ray machine isn't going to help you at all.
We're looking at a diagnostic landscape that is honestly incredibly murky.
Oh, it is the absolute definition of diagnostic muddy waters. I mean, you're dealing with overlapping symptoms, subjective reporting, just constantly moving targets.
Right, and that tension-seeking absolute precision in a totally messy world is exactly what we're getting into today. Welcome to the Deep Dive, by the way. Today we're pulling from a really fascinating stack of historical essays, scientific encyclopedias, and even some astronomy Q&A forums, all to uncover the story of Friedrich Wilhelm Bessel, which is such an incredible story.
It really is. For those of you listening, we are looking at a 14-year-old dropout who basically hated Latin, but who went on to measure the distance to the stars, accidentally pioneer modern psychology, and create a mathematical glitch that still haunts every introductory statistics student to this very day.
It's just an unbelievable trajectory, and what emerges from the sources on Bessel's life is this core theme that applies directly to anyone listening to this deep dive.
Yeah.
I mean, ultimate precision in life, in science, in data, it isn't about being perfect.
Right.
It is about a brutally honest accounting of our own imperfections.
Okay, let's unpack this. Let's go back to 1798. Bessel is 14, living in Minden, Germany, and he just walked out of school. He totally drops out.
Yeah, he was just over it.
Right, because the educational elite of the time insisted Latin was the only path to a real career, and he just couldn't stand it. Instead, he becomes a shipping apprentice at a firm called Kuhlenkamp and Sons in Bremen.
Which, ironically, is where his true education actually begins. I mean, he's not spending his small apprentice stipend on luxuries or anything.
No, he's buying math textbooks.
Exactly. Working in this highly pragmatic environment of global shipping, he realizes pretty quickly that international trade runs on mathematics. So he just starts teaching himself English, Spanish, and the really complex spherical trigonometry required for celestial navigation, just so he can better track the firm's cargo routes.
And if you think about it, navigating a 19th century cargo ship across a totally featureless ocean is surprisingly similar to mapping the featureless night sky.
Oh, absolutely.
You're trying to figure out exactly where you are in this vast, empty space using only points of light. And both of those things require an absolute obsession with reducing measurement error because, a tiny math error means your ship hits a reef.
The stakes were literally life and death.
Yeah. But I guess the question is, how does a shipping apprentice with no formal degree actually break into elite astronomy?
Basically, by doing the math better than the professionals.
Yeah.
And doing it on historically difficult data. So in 1804, Bessel got his hands on observation data of Halley's Comet that had been recorded nearly 200 years prior, back in 1607 by Thomas Harriot and Johannes Kepler.
Wait, calculating an orbit from 200-year-old data? That sounds like a total nightmare. You'd have to account for, the gravitational pull of planets shifting over centuries?
Exactly that. It's not just a simple ellipse. It's a path constantly perturbed by Jupiter and Saturn. And in his spare time, Bessel just recalculated the comet's orbit. He refined the numbers by mathematically accounting for those gravitational perturbations.
In his spare time?
Right. And his methodology was so incredibly precise that it caught the attention of Heinrich Olbers, who was a highly renowned astronomer at the time. Olbers immediately recognized the genius in the work and got it published in a major scientific journal.
Wow. And that fast-tracks him so much that by the age of 25, this former teenage dropout is appointed the director of the Königsberg Observatory.
Yeah, quite the promotion.
But of course, the academic elite of the time weren't exactly thrilled, right? The professors at the university didn't want an uncredentialed dropout teaching mathematics.
Oh, there was intense academic snobbery. I mean, he didn't have the pedigree. But Bessel had a very powerful ally, Carl Friedrich Gauss.
Who is basically one of the most legendary mathematicians in history.
Exactly. Gauss was so impressed with Bessel's rigorous approach to data that he personally intervened. He arranged for the University of Göttingen to award Bessel an honorary PhD in 1811.
Just a casual favor from Carl Gauss.
Right, and that effectively forced all the critics to just quiet down.
So now Bessel is an observatory director, and his mandate is literally to map the heavens. To do that, he needs flawless measurements. But as he dives into the data, he quickly realizes that his most expensive, crucial piece of equipment is fundamentally flawed. And the equipment I'm talking about is the biological one, the human eye and the human ear.
Yeah, and to understand why this realization was so disruptive, we kind of have to look at how observational astronomy was actually conducted at the time.
How exactly were they timing these stars? Because they didn't have digital timers.
No, they used something called the eye and ear method.
Huh.
Let's look at a really famous incident from 1796 at the Royal Greenwich Observatory. You had Neville Maskelyne, the astronomer royal, and his assistant, David Kinnebrook.
Okay.
Their job was to time the exact moment a star crossed a specific crosshair in their telescope.
So wait, practically, how do you do that accurately without a stopwatch?
Well, it is incredibly demanding on human working memory. The observer looks through the telescope, visually tracking the star's slow movement, but simultaneously they are listening to the loud, rhythmic ticks of a pendulum clock in the room.
Oh, wow.
Yeah, and they have to mentally divide the spatial distance the star travels between two of those auditory ticks to record the exact fraction of a second it crosses the line.
That sounds like trying to pat your head and rub your stomach while doing calculus in your head.
It requires immense cognitive load. It really does. And Maskelyne notices that Kinnebrook's timings are consistently 0.5 to zero point 0.8 seconds later than his own.
Now, for you listening in celestial navigation, an error of 0.8 seconds is huge. Because the Earth is rotating, an error in time translates directly to an error in spatial coordinates.
Right.
That 0.8 seconds translates to about 12 arc seconds in space, which could easily be the difference between a ship finding a safe harbor and crashing into the coastline.
Exactly. But Maskelyne viewed the human observer as a perfect, impartial tool. If the tool gave a different reading, he genuinely believed it was a moral failure.
So he assumes it's just laziness.
He literally wrote that Kinnebrook had fallen into a vicious way of observing, vicious spelled with a T back then, and he actually fired him for carelessness.
Wow, he fired him over a fraction of a second.
He did. But decades later, in the 1820s, Bessel reads about this Greenwich incident in a history journal and suspects something much deeper is going on. So he decides to run a controlled test. He and his own highly trained assistant, Friedrich Argelander, observed the exact same stars using the exact same eye and ear method.
And they find a gap of 1.223 seconds between their timings, which is a gap even bigger than the one that got Kinnebrook fired.
What's fascinating here is how Bessel interprets this data. He completely strips away the moral judgment. He proves that this discrepancy isn't laziness. It isn't a lack of skill either. It is an involuntary physiological constant.
A biological glitch.
Yes.
Yeah.
He realizes that every single human has an inherent unique delay in sensory coordination. The actual physical time it takes for the nervous system to bind a visual event with an auditory event and then mentally record it. Bessel terms this the personal equation.
Wait, so to fix a mechanical telescope problem, he essentially had to invent experimental psychology.
He really did. I mean, by defining the personal equation, Bessel transformed the human observer from this infallible judge of objective truth into a biological variable, a variable that needed to be calibrated.
So you couldn't just yell at someone to look harder.
Right. You had to actually measure an observer's specific cognitive delay and then mathematically subtract that constant from their data. And this idea was so revolutionary that it bled far beyond the walls of the observatory.
Where else did it show up? Because the sources mentioned it had a massive ripple effect.
Well, it became the foundation for understanding human perception.
Yeah.
In the 1870s, the pioneering psychologist Wilhelm Wundt used astronomical transit data to conduct the very first formal reaction time experiments.
No way.
Yeah, and later, the great American psychologist William James wrote extensively about the personal equation in his theories on how human attention and expectation literally alter our perception of reality.
And it even influenced Carl Jung, right?
It did.
Because in his development of analytical psychology, Jung expanded the concept of the personal equation to describe how an analyst's own subjective biases, like their internal complexes, their archetypes, inevitably color their perception of a patient.
Exactly. Jung argued that a therapist has to constantly examine their own psychological reaction time, basically, just to avoid projecting their own unconscious shadow onto the people they are trying to help.
That is so profound. So by figuring out how to calculate and subtract this biological noise of the human observer, Bessel calibrates his measurements to a degree no one had ever achieved. His data is finally clean.
Solace.
And because of that, he is ready to tackle the holy grail of astronomy, a distance problem that had baffled humanity for centuries.
Measuring the physical distance to the stars.
Right. And if you look at the historical sources, especially that astronomy forum detail, before Bessel, absolute geniuses like Isaac Newton and Christian Huygens tried to guess stellar distances by comparing a star's brightness to the brightness of Saturn or the Sun.
Which was a clever workaround, assuming that if a star was as luminous as our sun, you could just calculate how far away it had to be to look so dim to us on Earth.
But stars vary wildly in their intrinsic brightness, so those guesses were wildly inaccurate.
Completely. To get a direct physical measurement, astronomers knew they had to rely on stellar parallax.
Okay, remind us how parallax works again.
Sure, it's basically using the Earth's orbit around the sun as a baseline. You measure the geometric shift of a star against the background of space over a 6-month period. But because the distances are so unfathomably vast, the angles involved were just too microscopic for earlier generations of lenses to resolve. I mean, it's basic trigonometry, but the precision required was way beyond human reach.
Here's where it gets really interesting. Bessel knows how hard it is to detect that microscopic shift. So he doesn't just point his telescope at the brightest star in the sky, assuming it's the closest.
No, he's much smarter than that.
He uses strategy. He targets a relatively dim fifth magnitude star called 61 Cygni. Why? Because 61 Cygni had a very high proper motion. It was actually nicknamed the Flying Star because it drifted laterally across the celestial sphere much faster than its neighbor.
Which gave Bessel a totally critical geometric clue.
Exactly. For you listening, it's like standing by a highway. A car zipping right past you looks like it's moving incredibly fast, right? While an airplane cruising at 500 miles per hour up in the sky looks like it's barely crawling across the horizon.
Right, because of the distance.
Yeah, so Bessel realized that a high angular velocity meant this specific star was mathematically highly likely to be right in our cosmic backyard.
And luckily, he finally had the right mechanical tool to complement his calibrated biological tools. A Fraunhofer heliometer.
Wait, how does a heliometer work? Because the sources made it sound bizarre.
It was a total masterpiece of 19th century technology. Imagine taking a perfectly ground telescope lens, cutting it exactly in half down the middle.
They physically sawed the glass in half.
Basically, yes.
Yeah.
And then they used micrometers to slide the two halves slightly apart. This creates two overlapping images of the sky. By adjusting the halves until two different stars perfectly overlap in your field of view, you can read the micrometer to measure the angular distance between them. Yeah, with a precision that standard solid lens telescopes simply couldn't achieve. And using this, in 1838, Bessel announced his results. He measured a parallax for 61 Cygni of 0.314 arcseconds.
Just to picture that, an arcsecond is 1/36,000th of a degree. It's roughly the width of a human hair seen from 2 miles away.
And from that microscopic angle, using that basic trigonometry, Bessel calculated that the star was 10.3 light years away.
Which is astounding, because today, with modern satellite astrometry, we know the true distance is 11.4 light years.
Right, so using 1830s technology and his own calibrated eyes, Bessel was only 9.6% off. He physically expanded the known dimensions of the universe.
But the sources point out he wasn't actually the only one with this kind of data, was he?
No, he actually wasn't. At roughly the same time, Thomas Henderson had data for the star Alpha Centauri, and Friedrich Struve had data for Vega.
So why do we only hear about Bessel?
Because Henderson and Struve suffered from what historians call a failure of nerve. When they ran their numbers, the distances they calculated were so vast, so terrifyingly huge, that they basically assumed their instruments were wrong.
They just couldn't believe it.
Right, they delayed publishing. But Bessel had spent years calculating the flaws in his own eyes and his own instruments. He trusted his calibrated mathematics way more than his own human intuition. He had the math, and he had the nerve to publish it.
And trusting that math over human intuition led him to an even more radical conclusion. Because if you truly believe that mathematics can perfectly map the visible universe, you eventually realize it can also map the invisible universe.
Yes. This brings us to the discovery of the dark companions.
So Bessel was observing the brightest stars in the sky, Sirius and Procyon, and he notices they aren't moving in a straight line. As they move across the sky over the years, they had these tiny erratic wobbles in their paths.
Which is very weird.
Super weird. Now, a lesser astronomer might have blamed the telescope or, atmospheric distortion, but Bessel trusts his error correction. He deduces that these massive visible stars are actually being pulled by the intense gravity of unseen bodies orbiting them.
He's applying pure Newtonian physics here. Conservation of momentum dictates that a star won't just corkscrew through space on its own. It has to be orbiting a shared center of mass with another object.
Right.
If we connect this to the bigger picture, this was a massive philosophical leap. Up until this point, astronomy was entirely about observing light. But Bessel famously declared, light is no real property of mass.
That is such a cool quote.
It is. He argued mathematically that the universe could be filled with countless massive bodies exerting immense gravitational force while being completely devoid of light.
And he didn't just guess. He predicted the exact mass and orbit of these invisible companions in 1844. And it wasn't until 1862, 18 years later, and long after Bessel had passed away, by the way, that a telescope maker named Alvin Graham Clark finally spotted Sirius B.
Exactly where Bessel said it would be.
Right where the math said it would be. A white dwarf star, immensely dense but incredibly dim. He literally used the mathematics of gravity as a second set of eyes.
It proves that when you meticulously account for all your variables and biases, the equations will show you reality, even if that reality is currently invisible to human senses.
And this idea that we have to adjust our math to account for the limits of what we can actually observe is how Bessel's obsession with error correction still impacts every single listener today.
Oh, absolutely.
Because Bessel proved you couldn't trust a single observer or a single star. You had to look at samples. But as soon as he started looking at groups of data, he uncovered a mathematical glitch in how we measure reality itself. A glitch that shows up in every intro statistics class in the form of Bessel's correction.
Ah, yes. The infamous n-1.
When you calculate the variance of a sample, you are trying to figure out how spread out your data is from the average, but you don't divide by n, the total number of observations in your sample, you divide by n-1.
Which is always confusing to students.
Right. To a student, this always feels like a totally pedantic math trick, but it is actually a fundamental protection against the data lying to you.
To understand the mechanics of why this is necessary, you have to look at the difference between a massive population and a small sample. In the real world, we rarely know the true average of an entire population. So we take a smaller sample and we calculate a sample mean to estimate it. But mathematically, that sample mean is dangerously biased.
I always think of the sample mean like a tailor making a custom suit perfectly fitted only for the people currently standing in the room. By definition, the sample mean is the exact mathematical point that minimizes the distance to its own specific data points.
Yes.
It is tightly tuned to that specific cluster. And because of that, it makes the group look way more stable and way less variable than the general population outside that room actually is.
That's a highly accurate way to visualize it. In statistical mechanics, the deviations from your sample mean are called residuals. Because you are using the sample mean to anchor your data, instead of the true population mean, you lose what statisticians call 1 degree of freedom.
Meaning what? Practically, like in plain English.
Well, it means all those residuals, the distances from the mean, have to sum perfectly to 0. If you have 10 data points, the first 9 can be anything, but the 10th point is mathematically locked in to ensure they balance out.
Oh, I see.
So if you just divide the sum of those squared deviations by n, you are ignoring that lost degree of freedom. You will consistently underestimate the true variance of the population. Your data will literally tell you that the world is much more predictable and tightly clustered than it truly is.
Which is dangerous.
Very. So by shrinking the denominator, dividing by n-1 instead of n by Bessel provided a mathematical correction that slightly inflates the result, giving us an unbiased estimator for variance.
Okay, wait, I have to push back on this a bit. If we know that the sample mean is artificially shrinking our view of the data, why is the solution to just arbitrarily hack the denominator? Why not just find a better way to estimate the population mean in the first place?
Because you really can't. The sample mean is mathematically the most efficient, unbiased estimate of the population mean you have based on the data available. You can't magically invent data you haven't collected.
Fair point.
You have to use the sample mean, which means you have to accept that it is artificially pulled toward the center of your specific sample. The only mathematical way to correct for that specific gravitational pull is to adjust the variance calculation by exactly 1 degree of freedom.
Okay, that makes sense. So does dividing by n-1 completely fix the glitch? Like, does it make our data perfectly unbiased?
Sadly, no. And this is a crucial caveat that often gets glossed over. While n-1 gives you an unbiased estimate of the variance, it does not give you a perfectly unbiased estimate of the standard deviation, which is what most people actually use.
Right, because standard deviation is just the square root of the variance. Why doesn't the correction hold up when you take the square root?
Because of a mathematical mechanic known as Jensen's inequality.
Okay.
In simple terms, the square root of an average is not equal to the average of the square roots.
Can we put some numbers to that, just so I can picture it?
Sure. Think of it this way. If you have the numbers 9 and 25, the average of 9 and 25 is 17. The square root of 17 is about 4.12.
Okay, tracking.
But if you take the square roots first, the square root of 9 is 3, the square root of 25 is 5, and you average those, you get 4.
Ah, 4.12 versus 4. The curve of the math naturally pulls the number down. The operations don't commute.
Exactly. Because the square root is a concave function, it introduces a lingering downward bias. So even with Bessel's correction perfectly adjusting the variance, the moment you take the square root, your sample standard deviation still slightly underestimates the true standard deviation of the population.
So even Bessel, with all his obsession over eliminating error, couldn't make the math absolutely perfect.
No. And that is the ultimate enduring lesson of his work. Absolute perfection in measurement is a mathematical impossibility. We can never be perfectly objective observers, and our tools, whether they are brass telescopes or statistical formulas, can never be perfectly flawless.
We just have to deal with the mud.
Right. What we can achieve is asymptotic honesty about those flaws. We can measure the bias, we can apply the correction, and we can get incredibly close to the truth, as long as we never pretend the bias doesn't exist.
Which is a huge legacy. And, his obsession with modeling complex curves and correcting errors didn't just stop at stars and statistics. The sources mention it led to the creation of Bessel functions.
Oh, yes.
These mathematical tools that describe how waves propagate, which is literally why quantum physicists still use them today to understand the shape of atoms. And he also developed the Bessel ellipsoid, which is a mathematically corrected model of the Earth's shape that still forms the basis for GPS and mapping today.
It all stems from the exact same philosophy. True precision doesn't come from pretending our instruments, our brains are flawless. It comes from measuring the flaws. He basically took the human ego out of observation.
He really did.
By acknowledging that we are imperfect lenses, he allowed us to see further into the dark than anyone before him.
So what does this all mean? For Bessel, it meant discovering the true scale of the universe. But for you, listening right now, maybe it's a bit more personal. Think about Bessel using Newtonian math to see those invisible dark companions like Sirius B. He didn't see them directly. He carefully measured the wobbles of the visible stars around them. He looked at the effect to deduce the hidden cause.
Right. He observed the disturbance in the routine.
Exactly. So if you were to look closely at your own life, your daily routines, or your decision-making, what tiny unexplained wobbles might you notice? What are the recurring frustrations or patterns that slightly pull you off your intended path? And what invisible forces, uncalibrated biases, or personal dark companions might be exerting gravity on your choices without you even realizing it?
That is a question genuinely worth observing.
Keep your eyes open, calibrate your lenses, and don't forget to measure the wobble. Thanks for joining us on this deep dive.